Hello again. In this video we will be discussing the Weintek CODESYS PID library and the Weintek IR oven demo application. This demo was originally done in structured text, and I made modifications and added a program with the PID library usage and ladder logic. So let's get started. The development team at Weintek has come up with a few function blocks so far. A couple in particular I want to discuss today are the PID and PWM function blocks. PID, of course, is just a standard PID loop with auto tuning, and it actually runs beautifully. And then we've got a pulse converter function block here, so that you can take the analog PID output value and convert it to a pulse to use for heating, cooling applications without an analog input. So this project we're working with today is a hybrid of the IR application, IR oven application, that is available through support. And I made some modifications to it, and you will be able to get a copy of these files as well through Weintek USA support. So feel free to reach out to Weintek USA support and request a copy of these files. So we've got two programs running in this application. The original program that comes in the original demo app is just a PID, and it's all done in ladder, which is actually really nice. I did reproduce this program in ladder logic because that's what most people use, and the original part of the program is just these two rungs, so that's really all you would need to do a pulse output PID loop. I went ahead and added a few more things here to this. I added a linear transformation function block. I did this so that we could retain the 0 to 100 duty cycle or output from the PID. The output range is 0 to 100. I wanted to retain that so I could use either the pulse output, which is based on a 0 to 100 duty cycle, or I could use an analog output at the same time, and I can use this to scale the 0 to 100 to whatever my analog values need to be. And then of course I've got an error bit. And down here I'm just doing a move, which I can set this to that and move that to an analog output that I got in my rack here. I also made some changes in the PID loop variables, and I made some variables retentive, like the set point, and I reworked the way the run value works. So you have a choice in the project of whether you wanted to retain the run value of the PID loop on a power cycle or power loss, or if you wanted it to just be off at startup. So I put a little delay here to get the program up and running and all that before we tried to start the PID loop. There's actually, I think it was a 15 second delay. So those are the changes that I made, and I'll go over with you how I made them. I also made some changes to the Easy Builder Pro app. The original demo had allowances for only the structured text PID loop, and in the edited one, of course, I've added in the ladder, and I reworked some of the way the navigation works and some shortcuts On the structured text, the one that we have the retain run status, I've also, because the actual run status of the PID loop is not the same as the start stop register, so I added a little run light, and then I added a starting indicator while we're doing a delay on startup. This is the demo hardware setup. I've got an IR-ETH Ethernet coupler. I've got an AM06-VI analog I/O module. I've got an AI04TR thermal input module and an 8-in, 8-out digital I/O module with source output. I have two AC incandescent light bulbs with a thermocouple connected. I have the AC current isolated from the digital output with solid state relays. One other major thing I did different is I added another COM channel to access some special registers in the AI04TR module. I wanted to be able to access the temperature offset. As you can see, there's also other registers here that we could get to. We could switch it from Fahrenheit to Celsius if we wanted to. But I wanted to get to these offsets here so that we could also do thermocouple calibrations. So I added those registers in our slave module and then also created some project objects that could be used in our HMI application as well. Over here in our ladder program, you can see I've got a series of moves here, and I just wanted to do this in ladder so it was easy to understand. I've created some retentive objects called move values 1 through 4, and we're moving these values over into the offsets when the program's running. And these tags here are used in our over here in our HMI project, so you can set a thermocouple offset. So the actual process variable that is being read is pre-scaled to whatever our calibration is. I made this X1 object a retentive object, and if we have our retentive run function turned on, the value of this will be fed to the PID control bit, but only after our delay has timed out. And I made this long, like that, 15 seconds, for our demo purposes, to actually give the HMI and everything time to boot up and be running and everything. So, and of course, if that's turned off, then we will reset that run, the status of that run register on the first scan. In this run, we're doing a little bit of scaling. We're bringing in our thermocouple value as an integer. We're using real within our PID. So we're converting integer to a real value. I've got it in a temp register here. And then to convert that to real, all we have to do is divide it by 10. So that gives us our process variable for our PID. I also made the manual direction and auto tune inputs retentive. Down here we've got our PWM function block, and we've got our time period, which is preset up here in our variables. And then we are reading the MV value of our PID, this value. And we're giving and we're turning this X out bit on when our pulse is supposed to be on. And then I am writing that value over to our first digital output D0. So let's go ahead and get online so we can see some values working here. And I want to bring it up in CMT Viewer so you can see everything working. Right now we're working with our ladder PID. And I want to go in here to our setup page. And I want to go ahead and do a warm reset. I want to go ahead and set all these values to 0. And I want to do our PID set point at that light bulb's still a little warm. I'm going to go ahead and set it to 100 degrees. And the reason I did this, I want to show you how great the auto tune works. Go ahead and turn that on before I enable it. We'll go ahead and turn that on. Now it will have to, it'll run it at 100% duty cycle until it gets above the set point. And it will need to cool off and get down below the set point. Now you can see it's done auto tuning. It turned off automatically and it set all the PID parameters to what it needed to be. And you can see it holds a pretty nice temperature even with basically no thermal load whatsoever. I decided to go ahead and make a little hardware change. You can see here now I've added a little blower, simulate some thermal mass on our application. So I want to go ahead and I've got it connected. These are actually 12-volt fans, and I just wanted to hook them up to a digital output. And so I've actually got them linked together so we won't overvolt the fans. But I do want to go ahead and set it up on set up a little pulse output for that. So we'll go ahead and write that code together if you want. I'm going to go ahead and just copy these two rungs since we're doing that stuff anyways. I put them right in here, and I want to add a bit to, well, first of all I need to readdress this so I don't have a conflict. Make this 1. And the auto declare object will go ahead and just make that for us. And I want a run command for that, so I'm just going to call this about load. And we'll call this one about load out. And we want to be able to set a, we're going to use the same variables as before, so the time period and all that will be the same in the other one. So we're going to call this, how about load value? And that's a real object. So on this one we want our load out. Here we want to do D0, DO, I mean 7. And I'm going to go over here to my mapping, my digital outputs. I'm going to go ahead and log in. I'm going to do a full download. Go ahead and start. So let's test our fan real quick. We'll do a value of, let's start out 50%. And we want to tell it to load. Oh yeah, you can see there that's working. And turn that off. So I want to go ahead and load that, add that to our HMI project. So we'll go ahead and update our symbol configuration. So we'll go ahead and add these parameters to our project, our HMI project. So let's go ahead and add our load function to our HMI project. Home tab, system parameters. We want to go ahead and import our new tags. I'm just going to recycle these objects here. Find our tag. Oh, I want to set a limit. Zero to 100%. Our load tag. So let's go ahead and download our project. Test all this neat stuff out. Since we just did a program download, we need to, even though that's retentive, we still need to set that value. I'll go ahead and start out at 50% on this one. So you can see how fast it's climbing. Let's turn our load on. See, it's struggling a little bit more. Slow that down a little. Pretty neat. I'm gonna slow our thing down even more, about 15. ahead and do another auto tune. And this is in real time. I'm not speeding the video up or slowing it down or anything. And that's all it took to auto-tune it. This library works beautifully. I encourage you to contact Weintek USA support or sales for a copy of the library and the video related files. Thanks for watching, and be sure to come back and see more of our videos.